Okay, my name's Gavin Thompson from the Happold Foundation and from Bureau Happold. Welcome to the IET. You are very welcome. I've just got to run through a couple of quick housekeeping things before I forget. If there are no planned fire alarms tonight, so if the fire alarm does go off and you hear it for more than 20 seconds, you need to leave the building by the way that you came in, which is out of the exits at the rear, through the main door, and the assembly point is under the bridge to your left. And if you need the washrooms and things, they are down in the basement on the stairs to the left and the right. Okay, I'm not going to take too much of the time because we've got quite a lot to get through this evening. I chair the Happold Foundation. It's a charity. It's supported by the partners of Bureau Happold, and its goal is to promote the role of engineering in society. Not just to make society aware of what engineering is, but to encourage people to enter the profession of engineering, and also to encourage those who are in engineering to step up to the plate and influence society over the key decisions that society faces that are important for its future. As engineers, most of us are not that well equipped in the communication side of things, and we, Ted Happold, our founding partner at Bureau Happold, used to say, "Can you hear me at the back?" And when he said, "Can you hear me at the back?" he was talking to the engineers who always sat at the back and were a little bit shy of coming forward. And so the Happold Foundation is all about encouraging those people at the back to step and come and sit in the front row and influence. We have 3 focus areas: urbanisation, scarcity of resource, and climate change. And so for this, the 2016 Happold lecture, we were delighted to be introduced to Emily and for Emily to agree to give this lecture because it fits perfectly with one of our 3 focus areas, climate change, and also coming on the back of the recent Paris talks and a number of different natural disasters that have occurred and are occurring around the world. It seemed perfect for us to be hearing from Emily and from the panel who are going to join us on the stage afterwards to debate what Emily talks to us about. It seems perfect to be talking about that today and for the engineering community to be thinking about how it can influence that area. So if I can hand over to Emily, thank you very much.
Thank you, Gavin. So thank you very much for giving me this opportunity to speak to you this evening. I thought I'd start by showing you a few images from my work in Antarctica. I'm a climate scientist, and my plan for the next hour is to take you on a tour of some of the scientific evidence that underpins our understanding of climate change. This is our planet. We only have one of them. And one of the things that becomes very obvious when you start to understand it from a scientific perspective is just how interconnected the different systems in our planet are. The polar regions are intimately connected with us in the UK, and changes there have an impact on us here. And that follows through in terms of connectedness with the Earth's ecosystems, and then with the systems that affect us more directly, our food systems, our water systems, and our energy systems. So one of the things that I'm going to stress repeatedly throughout this evening is the importance of understanding those interconnections. And we do that as scientists through going to places like Antarctica and taking measurements to try and understand the key processes. One of the things that my colleagues did was look in detail at the processes affecting the ozone hole and brought the world's attentions to the ecological problem associated with that. Now, our main focus is understanding climate change and understanding how human activities are driving the Earth system into a different space. As Gavin said, last year heralded a great breakthrough in terms of the Paris Agreement, which is likely to be ratified in New York next month. And what I want to do over the next hour is outline some of the key science evidence base that underlay the call to action that was responded to in Paris. So I think the key message that I want to give is that we may still be in for the worst of times. I'm certainly going to outline some of the key threats that we're facing, but I also want to emphasize that there are opportunities here too. And I think that particularly as engineers, you stand in a position to respond to those opportunities and try to take us to a stage of development where we embrace new technologies and try to avert potential disaster. So, Paris Agreement in December was a rousing success, especially compared to previous such events. And what I thought I would do is structure my comments around that Paris Agreement and statements from that. So here is one of the key initial statements, and the text of the Paris Agreement comes with a huge section of preamble, but one of the key statements in that preamble is this, that recognizing climate change represents an urgent and potentially irreversible threat to human societies and the planet, and then it goes on. So I thought I'd start off by unpicking that statement. What you see here in the graph is the average temperature of the surface of the Earth, average across the entire surface of the Earth, and it's a time series from 1850 through to the present day. If you look in detail, you can see that there are three curves on there because there are three different analysis data sets that are brought together worldwide, but they're very much in agreement with each other. And the overall message is that currently today, 2015, was about 1 degree warmer than before the Industrial Revolution started. You can see that there's a lot of year-to-year variability. There are periods when the temperature has been warmer for a year or even for a decade, or periods when it's been cooler for a year or even a decade. But the overall trend is one of an increase. And it's not just the global average surface temperature. There are many other variables that we can look at, indicators of the Earth system where we're seeing strong change. And here's just another. At the bottom is the global average sea level. A significant increase again from the 1800s through to the present day. And these data sets, and I could have put up here any number of other ones, Arctic sea ice, for example, or the amount of heat that's stored in the ocean. These data sets are gathered through a huge different variety of sources. Some of them, at least in the recent period, come from satellite data. Others come from scientists such as myself going down to places like the Southern Ocean and you know, almost literally sticking a bucket over the side of the ship to see how the waters are changing. Now, what's been driving those changes that we've been seeing in our Earth system? Well, here are two other graphs showing strong changes since 1850 to the present day. The first top graph that you see is global primary energy use. And just since the 1950s, there's been something like a 5-fold increase in primary energy use throughout the world. And that has driven a dramatic increase in carbon dioxide levels. Carbon dioxide levels at pre-industrial times were around about 280 parts per million in the atmosphere, and they're now up at 400 parts per million, a dramatic increase. And again, you can see if you look at these curves, 1950 or thereabouts seems a particularly sort of a particular point at which you see these dramatic changes. And a number of people have suggested that somewhere around there might be the marker of a new geological era. And in fact, there is going to be a debate within the International Union of Geological Sciences later this year to determine whether or not we can define a new geological era of the Anthropocene. I wanted just to take you back in time a little bit before moving forward in time, just to put this in a much longer term context, and also to understand what warning signs we can gain from looking at the past history of the Earth. So this graph comes from the record of temperature from ice cores in Greenland. The present day is on the right-hand side here, and if you go back across to the left-hand side, it goes back 50,000 years, well into the last ice age. The vertical axis is temperature. And so there are two important things that I want you to take away from this graph. The first is the Holocene, the period of time in which we've developed society, really the time since agriculture was first invented by humans, and we started to group together and form early societies. You can see that our climate has been very, very stable. There's been rather few temperature fluctuations, at least in this temperature record, which is reasonably representative of the Northern Hemisphere. As you move back in time, though, you can see that in the past there have been periods where the temperature has fluctuated really violently. Indeed, there are periods when we've seen 10 degrees of temperature change in less than a decade. So, first of all, our intuition about the climate being relatively stable is being gained from a rather short period of the Earth's history. In fact, the more normal state, in some sense, at least for the Northern Hemisphere, has been one of much more fluctuating temperatures. But the other lesson from this is that the Earth system is such that it can flip in temperature very dramatically. There's still a lot of research to try and understand what's driven these Dansgaard-Oeschger events, where you get these very strong temperature changes. But some of the more recent hypotheses have suggested that a key factor is an increase in the amount of heat from the Atlantic into the Arctic Ocean, and then that interacting with the sea ice in the Arctic. And if that was the key process, then that's a process that could occur again today. So it's a salient warning of the possibility of very dramatic and abrupt changes in climate. Now, one of the key questions that was asked of the Intergovernmental Panel on Climate Change was how much influence have humans had on the change in climate. So I've shown that we've seen an increase in temperature of about 1 degree from pre-industrial times, but how much of that has been due to human influence? And this is a plot that tries to answer that. The black bar shows the observed warming since 1950, and the orange bar shows the amount that's been assessed through multiple different lines of evidence as being the contribution from all of man-made pollution. And that divides up into two competing contributions. There's one contribution from greenhouse gases, and there's a contribution that acts in the opposite direction from aerosols, from soot, that has a cooling effect on the atmosphere that we've also been putting into the atmosphere. So combined, the two equate to almost explaining the entire observed warming, and led to the Intergovernmental Panel on Climate Change making the statement that it's extremely likely that human influence has been the dominant cause of the observed warming over the last half century. You can ask about other natural changes in the Earth system, of which there are a number. So if there's a large volcanic eruption, particularly if it occurs close to the equator, the dust from that volcanic eruption can go up into the atmosphere and affect the climate for a number of years afterwards. But in terms of the long-term trends, it's not a significant factor. And variations in the sun's output can also have a change in our temperature. But over this time period, that hasn't been a significant factor either. So I want again to look back into the past to understand a little bit more about how unusual our present climate state is compared to our historical past. I've already shown you some results from ice cores in Greenland. In Antarctica, we can go much further back in time and understand what the climate was even further back into the past. And what I've shown you here in this photo is a slice through an ice core. And I just wanted to explain to you how we're able to determine climate so far back in the past, because to me it's really quite remarkable. These ice cores are almost like a museum of the past. What you can see are the tiny little bubbles of air. And what happens is that the snow falls in Antarctica, and as it falls, it traps air from the atmosphere at which the snow was formed. And then as the snow falls layer upon layer in Antarctica, it means that as you drill down through the ice, you're able to go back into the past and actually sample the air that was actually in the atmosphere many hundreds of thousands of years ago. And this is the sort of data that we're able to obtain. On this graph, the present day, again, is here on the right-hand side, but we go all the way back almost 1 million years, 800,000 years at the left-hand side. And the top is showing the temperature changes, and in the bottom, the carbon dioxide changes that we're able to determine from these air samples. And you can see that over this whole million years, the carbon dioxide and the temperature have varied pretty much in sync with each other. I wanted just to give you an indication of quite how far back in time 1 million years is, because it's difficult for me to get my head around this. So right at the start are some of the earliest human tools. One of the earliest objects in the British Museum here is from around about 1 million years ago. Neanderthals were sharing the Earth with us until around about 250,000 years ago. And this covers many, many, many different states of the climate system. So if we go back to the last ice age, sea level was about 120 meters below where it is today. If we go back to the last period of particularly warm temperatures, sea levels were between about 5 and 10 meters higher than they are today. So very dramatically different states. Now, if we look at where we are at present, if we look just at the carbon dioxide, and I put that 400 parts per million onto that graph, you can see just how far out, at least in terms of carbon dioxide, we are from the natural system over that last million years. So I now want to turn to the next bit of this statement about the urgency in terms of the way that the system is changing. This is a photo from the Canadian Arctic from a place called Iqaluit. I visited a few years ago and spoke to a number of the people who live there. It's really a sort of desolate outpost of the Canadian Arctic. You can see the Hudson Bay there in the background. The Arctic has seen more warming than elsewhere on the planet. The warming that we've seen, I've shown you pictures of the global average, but that hides a lot of regional detail. And the warming in the Arctic has been extreme. I'll come on in the next slide to show you how the sea ice in the Arctic has been changing. But in areas like this, there's been dramatic changes as well. And whereas for you and I, except for perhaps an increase in flooding events that we've seen particularly in the UK in recent years, we haven't really seen the climate change significantly with our own eyes. But people living up in the Canadian Arctic have. And you just have to speak to any of the people up there and they'll immediately tell you stories of how the Hudson Bay used to freeze in a way that it doesn't freeze any longer, and how that's directly impacting their lifestyles, which are so intimately tied to the ice. So in terms of the Arctic sea ice, here are two satellite pictures, one from 1992 and one from exactly the same day of the year in 2012. The pink area is the area of sea ice. This is taken in September at the end of the summer melt season. And you can just see just how dramatically the difference in sea ice between those two snapshots, which are only 20 years apart. And if you're not used to seeing maps of the Arctic, it's difficult to really visualize quite how large an area it is. So I've included here a map of Europe, and the equivalent amount of Europe that would be wiped out if the same amount of Europe was lost as we've seen loss of sea ice. And I think that really brings home quite what a major difference it is. Some of the people in my research group back in Cambridge are looking at the moment to try to understand what the wider impact was. So in some of my opening remarks, I said how interconnected the Earth system is. The sea ice is very, very reflective. It's a very reflective white surface. If you remove it, you've left behind dark ocean. And you've also changed from a situation whereby the sea ice essentially prevents the atmosphere and ocean interacting together. You remove it and the atmosphere and ocean are directly interaction with each other. And so the question is, what's the knock-on effect of this change in sea ice? And we're starting to have a greater understanding of the way in which that is likely to impact weather in the UK and the rest of in Europe and in the United States and North America. So I wanted now to say a few things about some of the major weather events that we've seen around the world in recent years, as Gavin noted at the start, and the dramatic impact that they have had both financially and in human terms. In 2003, we saw a major heat wave in Europe, and it's estimated that there were 70,000 premature deaths across Europe as a consequence of that heat wave. And we've seen many other extreme events over the last decade or so. Some of them may be related to climate change, some not, but all give a strong indication of how variation in weather can have a dramatic impact on people's lives. And I thought this was a particularly strong example that showed how a weather event can have severe knock-on impacts. This is an electricity substation near Gloucester that came very close to being taken offline in the floods in 2007. And a major operation was mounted involving the army to sandbag this whole area. And then subsequently, a very expensive flood defence system has been put in place to try and prevent this happening again. Now, the important thing about this electricity substation is not only did it provide power to some 500,000 homes, and so 500,000 homes were at risk of going offline, potentially for many weeks before new parts could be brought in. Allegedly, GCHQ is also connected to this, but I suspect they probably have a backup power supply somewhere. But the other thing is that you can see that very close to this electricity substation is a major road. If that road had also been flooded and damaged, then it would have made it even more difficult to bring new parts in to repair the electricity substation. So you can start to see where you get knock-on effects. The electricity substation also powered nearby water treatment plants as well. So again, you can start to see the knock-on effect. So this interconnectedness and the potential for real systemic risk is significant. The World Economic Forum each year puts together a survey of what people consider to be the greatest global risks, and this is the results of the survey from 2016 from the most recent meeting in Davos. What they really highlight each year is exactly this, the interconnectedness of the risks. The number one risk that the survey produced this year was failure of climate change mitigation and adaptation. But if you look at the things that are immediately interconnected with that, water crisis, food crisis, biodiversity loss, and I guess a controversial but worrying potential connection in terms of large-scale involuntary migration. So I wanted to return to just a few of these examples to ask the question, well, we've seen these major weather-related events, but can we say anything about how much more likely those events have been as a result of the climate change that we've seen to date? And I'm going to take the example of the heat wave that we saw in 2003. And here at the bottom is some data that speaks to that question. So the background risk before climate change of having a very strong heat wave in Europe was, let's take it as being less than 1 in 1,000 years, and that would be the distribution of summer temperatures. By the 2000s, when we actually saw that very hot summer in Europe, then that whole curve had shifted such that it was less unusual to see such a hot summer. And in fact, the chance of having a heat wave was reduced down to 1 in 50 years. But the temperature in Europe has been increasing even since then. So if we redo that calculation today, we now find that the risk of having a heat wave in Europe has shifted to being 1 in 5 years as that curve has shifted along. So what was once a 1 in 1,000 year risk is now a 1 in 5 year risk. That's a really dramatic change in odds as a result of the climate change we've had to date, let alone what we may be in store for in the future. And as we move to look at other weather-related events that have occurred, just let's take 2014, then we see this repeated story that the chances of having these weather-related events has already dramatically increased as a result of the climate change that we've already observed. And here are just a few of the examples. The floods that we saw in the UK in 2014, a change in the likelihood of having those sorts of weather patterns. There's been a severe drought in the southern Levant region, which has complicated the refugee crisis in that part of the world. And again, record-breaking temperatures that are more likely as a result of the change that we've seen to date. And actually, China has seen a number of very severe weather events over recent years. This example here was of a drought in northern China with very extreme hot temperatures and big impacts on agriculture, estimated to have been an 11-fold increase in risk as a result of the climate change that's already been observed. So these are some of the weather events, but there are also other big changes that we've been observing in the planetary system, particularly in the Antarctic, which is my area of speciality. And there's a particular concern that goes back to some of the earliest comments that I was making about the potential of the Earth system to undergo very dramatic changes. The whole of the western side of Antarctica is covered with an ice sheet that is grounded below sea level. And there's therefore a possibility that the sea could encroach underneath that ice sheet and lift it off and contribute significantly to sea level rise. Perhaps 3 meters of sea level rise over a period of time, we're not sure. It might be centuries, might be longer, might be shorter. And there's evidence that's starting to come from colleagues of mine that suggests that some of the key glaciers that feed this region may already be in unstoppable retreat, and therefore we may already be on an irreversible course for that ice sheet to collapse. There's large amounts of uncertainty, but again, looking back at the historical record, we know that the ice sheet hasn't always been there in the past. And across Antarctica, we're seeing evidence of large collapses in ice sheets. And here is, I just wanted to show you this video. This is a colleague of mine who was in Antarctica in 2008, flying over this ice sheet, the Wilkins ice sheet, and wasn't expecting at all to see the ice sheet suddenly collapse, but that's what happened, literally in a matter of weeks. What you're seeing here is the front of the collapsed ice sheet. This is the height of a 15-story building, and that's just the amount of ice that's above the sea. You can imagine the amount that's beneath the sea on top of that. And the area of this ice sheet that collapsed, as I say, in just a matter of weeks, was about the size of Greater London, a huge area that's disappeared. And these things are, essentially irreversibly collapsed. It takes a very long time to grow an ice sheet, but a very short amount of time for an ice sheet to collapse. So I wanted to move now to talk a little bit about the future and the future projections. These are projections that are based on climate model simulations of the future. And we input into them different scenarios in terms of what our future emissions of key greenhouse gases might be into the future. And what's shown on this figure here are the temperature changes from now out to the end of the century under two possible scenarios. One, a business as usual scenario where we continue to emit greenhouse gases in much the same way as we are at present. And another one, which is an aggressive mitigation scenario where we go above and beyond what's been committed to already in Paris to reduce our emissions still further over the course of the century and to keep our temperatures below 2 degrees or approximately 2 degrees centigrade increase with respect to pre-industrial times. I've put up here at the same time as this graph a photograph of one of my daughters and my grandmother, because I spend all my time looking at graphs like this, and it's very easy to forget that these aren't just graphs, these are predictions of the future. My daughter is going to be the age of my grandmother at the end of the century, so this is essentially her lifetime, and she might be following the blue curve or she might be following the red curve, and her life is going to be very different depending on which curve we as a society choose to follow. And I think it's important to remember that these aren't just graphs, these are millions of people's lives. Again, to put this in the historical context, this is an estimate of the temperature that we've seen over the last 1,000 years, last millennia. That's when the Tower of London was built by William the Conqueror, and you can see that the temperatures have remained relatively stable since then, and that's what those temperature changes look like on the back of those changes. I think that brings into context just quite how dramatic changes we are projecting. And notice that even under this best case scenario, even under the blue future, we're still taking the world into a world that's not been seen, certainly for the last millennia. Now, if we look at how that maps onto things that affect us, global average temperature is not something that affects any individual, but it is an indicator of the level of change that we're likely to see in aspects that do affect individuals. And this curve, this graph is supposed to encapsulate some of that information. So if you look, for example, at unique and threatened systems, or at the risk of having extreme weather events, or at the risk of a large-scale, abrupt change in climate of the sort that I was indicating have happened in the past in the polar regions, then as you increase the temperature, then you increase the risk of all of those occurring. Of course, the risk that an individual sees depends on where they are and what things affect them. And so this is only an indicator of the level of change. If we want to try and understand what a business as usual world would look like, well, I think it doesn't take me to articulate this. It's the sort of things that you would imagine: dramatic sea level rise compared to the present, real challenges in terms of water scarcity and in terms of food production, breakdown of resource supply chains, potential threats in terms of large-scale migrations, mass extinctions of species, and then effects on other aspects such as our human health. Just to put some concrete numbers behind some of that, here is the implications in terms of sea level rise, and then the knock-on effect of that in terms of coastal flooding. So under these two different futures, the business as usual future in red and the aggressive mitigation future in blue, you can see on the left there the projections in terms of sea level rise over the course of this century. Under the business as usual future, the sea level rise might be up to a metre higher by the end of the century. But when you map that onto the number of people exposed to flooding, and in particular when you take into account projections in terms of what we're already seeing of large movements of people into coastal cities, particularly in Asia. Many of those coastal cities are already severely exposed to coastal flooding. Then we find that under that business as usual feature, there's between a 7 and 25-fold increase in the number of people exposed to flooding over the course of this century. London has the Thames Barrier to protect it from flooding. That was built in 1982 to withstand a 1 in 1,000-year flooding event. But if there was a metre of sea level rise, that would reduce down to be only protecting London for a 1 in 10-year event. But if you look around the world, many of the world's major cities are located in coastal regions. San Francisco, for example, if you look at a map of San Francisco, you very quickly realize that the major airports, the road systems, the railways, and many of the key power stations are all located in coastal regions and at risk of 1 metre of sea level rise. And if you turn to Asia, I already mentioned there are an increasing number of large megacities in Asia that are located in coastal regions. It's estimated that 150 people are already exposed to coastal flooding in Asia, and just with a 30 centimetre rise in sea level rise, that could more than double. So that statement from the Paris Agreement then went on to talk about the urgency of addressing climate change. So I thought I'd now say a few things about that. How much time do we have to try to address moving between being on the red curve to hopefully being down on the blue curve in terms of our future? Well, the science indicates that to have a likely chance of staying below 2 degrees centigrade, we have approximately 30 years left of burning fossil fuels at our current rate before we've used up our entire budget of what we can put into the atmosphere in order to be able to stay below that level. Actually, the Paris Agreement, as I'll come on to say, in the end agreed that we should try to stay well below 2 degrees centigrade and aim for 1.5 degrees centigrade. So you can ask the same question: how much do we have left of burning fossil fuels at our current rate before we've used up all we can burn to stay below 1.5 degrees centigrade? And it's actually a difficult calculation to do because it ends up being such a short time scale, but it's something like 10 years at our current rate of burning fossil fuels before we'd have to stop entirely if we were going to be able to stay below those levels. Now, this is what current emissions look like. Carbon dioxide emissions globally, and then broken down into some country estimates. And there's been a great fanfare because actually the last couple of years emissions haven't increased dramatically in the way that we've seen over the previous decade. So the hope is that this is an indication that emissions have started to plateau and that we might have started to be able to move in the direction downward. It's only 2 years, and you can just see, looking at this graph, that there've been other plateaus in the past, so I wouldn't want to store too much on it. Perhaps the main thing, if you trust the data, and there's some question marks over the data, is that there does appear to be an indication of a decoupling of these emissions from GDP, which would be a very positive sign. This is a map. The data comes from 2010, but you would see pretty much the same map if you look today of where those carbon emissions are coming from. And, well, you can try and assess where you think the hotspots are. But one thing that you can really notice is that the hotspots tend to be in the areas where there are large megacities, and cities contribute a significant amount of carbon emissions, which is both a problem but also starts to lead to you thinking of potential solutions. More than half the global population live in cities currently, and that's expected to grow to 70% by 2050. Currently, cities account for about 70% of global energy use, and if you look at the whole of greenhouse gas emissions, they account for about 80% of greenhouse gas emissions. So they are undoubtedly an important focus both of mitigation and adaptation solutions, as I'll come on to describe at the end. I just wanted to emphasize this in passing, that the story of greenhouse gases isn't just about carbon dioxide, it's also about other greenhouse gases such as methane and nitrous oxide. And in particular, methane, which is the plot that you see in the middle, and that's the amount of emissions, the amount of methane in the atmosphere from the graph going from 1985 to the present day. And what you can see is that the methane in the atmosphere has started to level off in the early 2000s, but then since then it's been dramatically increasing. Methane is 25 times stronger greenhouse gas than carbon dioxide, so the fact that it's dramatically increasing is important, and we don't fully understand the reason. We don't understand whether it's coming as a result, as a byproduct from some oil and gas exploration, or whether it's coming as a feedback from tropical wetlands, or indeed in the Arctic. And so that's a topic of significant current research to try and understand why that methane is increasing so dramatically, because it's potentially very important. Right, the Paris Agreement, and this seems to have been a bit mangled. I hope that's not an indication of the Paris Agreement itself, but there were two key articles that spoke to the science in the Paris Agreement. The first one concerned the statement about keeping temperatures to well below 2 degrees with the ambition to keep them below 1.5 degrees centigrade increase. And the second talked about peaking greenhouse gas emissions as soon as possible and then achieving a balance between the anthropogenic emissions by sources and the removal by sinks of greenhouse gases. So essentially reaching net zero greenhouse gas emissions over the course of the century. So why are those two things important? So let's take the temperature thresholds to start off with. Here's just one example. I could have picked any number, but I've just picked an example based around ecosystems. So at 4 degrees centigrade temperature increase with respect to pre-industrial levels, it is estimated that a quarter of mammals and half of all plant species are likely to lose half of their suitable habitat by the end of the century. If we keep temperatures below 2 degrees, then those impacts are more than halved. And that's a repeated story across any dimension that we look at. The impacts aren't linear. The impacts that we see at 4 degrees are typically more than double the impacts that we see at 2 degrees. And we really do gain significantly by keeping the temperatures at that lower level. What about 1.5 with respect to 2 degrees? Well, there are a number of indications from the science that it really would be safer to keep things below 1.5 degrees centigrade. And here are two examples. The Greenland ice sheet, we know in the past that the Greenland ice sheet has not been there in large part. And we know that the amount of ice on the Greenland ice sheet at present could potentially contribute 7 meters to sea level rise, again over a long period of time. And we suspect that the threshold for the Greenland ice sheet either being there or not there is somewhere in the zone between 1.5 and 2 degrees centigrade of continued increase in temperature. If we look at other impacts, then we similarly see a significant change between 1.5 and 2 degrees. And here are just some of them in terms of coral reefs, in terms of UNESCO World Heritage Sites, in terms of increased river flood, for example, all have significant increase in impacts between 1.5 and 2 degrees centigrade. Now that might be all very well, but what hope do we possibly have of keeping temperatures below 1.5 degrees centigrade? And these two plots try to assess that. The top plot shows, since the 1950s up to the present day, in the black line, the actual observed temperatures. In the coloured yellow and blue lines are just extrapolations of the trend of that, to see where the trajectory we're on. And in the red hatched is a more sophisticated forecast of the temperature over the next 2 decades. But whether you take a sophisticated approach or just a brute force drawing a straight line approach, you can see that there is a significant risk of us reaching 1.5 degrees temperature increase in the next couple of decades. So that doesn't look so hopeful. The bottom plot shows some analysis of that aggressive mitigation scenario that I previously showed you. That shows that there is some chance of keeping temperatures below 1.5 degrees centigrade. And in fact, if you increase the ambition even beyond, above and beyond the aggressive mitigation scenario, and add in what the maximum possible you might be able to do, and some people think it's not even technologically feasible, in terms of action on additional climate pollutants, then it gives you a bit more of a chance of staying below 1.5 degrees. So it seems as though it's right at the edge of our technological feasibility. And there's another big challenge associated with it, which is that any of the scenarios that give us any hope of keeping below 2 degrees, let alone 1.5 degrees, require a significant deployment of what are known as negative emissions technologies. This is essentially taking carbon dioxide out of the atmosphere. And the challenge of that is that there are lots of side effects associated with that. Side effects in terms of impacts on water resources, impacts on food security, impacts on biological systems, depending on what type of technology you adopt. And so the whole system together needs to be taken into account to understand whether this is achievable and indeed desirable. So, a key aspect of the Paris Agreement was this statement about achieving net zero greenhouse gas emissions at some stage in the second half of the century. In terms of where the science stands at the moment, and there's active efforts at the moment to bolster the scientific understanding of this, but the estimates of the moment are, in terms of carbon dioxide emissions, to have a likely chance of staying below 2 degrees centigrade, we need to reach net zero early in the second half of the century, and for the full suite of greenhouse gases, net zero, certainly before the end of the century. For 1.5 degrees centigrade, those numbers are brought dramatically further forward. And there's considerable uncertainty on the exact dates, but somewhere around 2050 maybe earlier, in terms of net zero for carbon dioxide. In Paris, almost all the countries submitted pledges in terms of how they intended to reduce their emissions over the coming years up to 2030. And so an assessment was done as to whether or not those pledges were sufficient to keep our temperatures below 2 degrees centigrade. And the resounding answer was that they weren't sufficient, although they certainly set us on the right path. You have to make significant assumptions as to what countries might do post-2030 to determine what ultimate temperature we might reach. And so there's no one answer as to what Paris achieved in terms of the country's pledges of our future temperature. But the estimates lie somewhere in the range of 2 point quite a lot to 3 point something. So around about 3 degrees centigrade as opposed to the 2 degrees that we're, or 1.5 degrees that we're aiming for. Right, in the last section, I now want to come on to talk a little bit about what we could do about all of this. So I kind of laid out the challenge. We're already seeing significant climate change even today, but there's a potential for very dramatic changes in the future if we don't move from the business as usual red curve onto the aggressive mitigation blue curve, or even below it. So how are we going to do that? Many of you might have read David Mackay's book on sustainable energy without the hot air, and that's now been turned into a global calculator, which is one attempt to try and estimate how we might do it. And you can all go and play with the global calculator should you wish to. Here is some of the analysis that come out of that. There was a report that was produced using it, Prosperous Living for the World in 2050, insights from the global calculator. And I should say that these insights come with a very big caveat that this is just one model. But here are the three main conclusions that they had in that report. That yes, it is physically possible that all 10 billion people that are estimated to be in 2050 could live in a world where they're eating well, travelling more, living in more comfortable homes, whilst at the same time reducing emissions to a level that's consistent with a 50% chance of no more than 2 degrees centigrade warming. But, and there's a big but in this, to do so we really need to transform the technologies and fuels that we use. And transform in this really means major transformation. And even that's not sufficient. We also need to make much smarter use of land resources and to expand our forests. You basically have to do everything. And in fact, actually, the land resources are particularly key lever in producing a world in which you meet this 2-degree target. And another thing that I want to stress in terms of the challenge of all of this is that, as you might have noticed from some of the earlier graphs that I showed, even that blue aggressive mitigation future is a significant change with respect to what we've seen over the last millennia, for example. So even in the best case scenario, there's still going to be significant changes that we're going to need to adapt to. So if you sort of think of the total climate risk being that red bar on the left-hand side, then mitigation in the form of us reducing our emissions might reduce that risk to something like the orange bar. But even if we do really aggressive mitigation, there's still going to be some remaining risk that we're going to have to try to adapt to, that we might want to try and be prepared for. And then finally, there's going to be some risk that's simply unavoidable that we're just going to have to take the hit on. So that's one way of looking at the problem. Another way of looking at the problem, which is equally important to think through, is that many of the actions that we might take in terms of mitigation and reducing our emissions, or in terms of adaptation, building resilience, are also likely to have significant co-benefits. And I think people are increasingly starting to think about those co-benefits, both in terms of building economic cases for responding to climate change, and in terms of thinking through the whole systems approach that I have been trying to outline in terms of the interconnectedness of the system. I wanted just to talk through a little bit an example. I mentioned earlier the importance of cities in terms of their contribution to greenhouse gas emissions. So clearly cities have the potential to play a significant role in terms of mitigation, and indeed the way that a city is set up in itself lends itself to mitigation solutions that bring in buildings, energy, transport and industry on a level that can only be achieved in a city context. And at the same time, if we move down this risk response in terms of adaptation, building resilience, there are also significant opportunities that exist in cities in terms of resilience of the water systems, the food systems, the energy and transport systems. But there's equally a strong caveat that needs to be brought to bear in terms of that consideration that well-governed cities with universal provision of infrastructure services and so forth provide a strong basis for such an adaptation and mitigation response. But many of the rapidly developing cities in developing countries where many of the large megacities are starting to develop simply lack the required financial, technological, institutional and governance capacity in order to be able to respond. And many of the impacts that they might see in terms of future climate change may worsen the access to basic services and quality of life. So although we can come up with scenarios, theoretical scenarios of a world where we can live in better homes and eat better and travel more and at the same time reduce our emissions consistent with a 50% chance of 2 degrees of warming, the harsh reality of the real world may be more complicated than that. So I'm going to bring things to an end there. I started off by talking about the fact that some scientists are contemplating defining a new era, new geological era, the Anthropocene. And to my mind, we're really at a point now where we are in a position to define what that Anthropocene may look like. Its initial path might have been one of dramatic changes in our climate, largely influenced by our human activities. But how we move forward now is going to depend on our response to that. I've indicated some of the great changes that we might set off in terms of changes to our entire planetary system, from collapsing ice sheets in Antarctica or other abrupt changes that we know have occurred in the past and we could trigger off like an avalanche occurring in the future. But it's also within our bounds, and particularly speaking to an audience of engineers, to instead of looking at this as a threat, to look at it as an opportunity and to try to move to define the Anthropocene instead of by the great calamity that we as humans have caused to the world in which we live. Instead, the great innovation opportunity that we've seized in terms of moving ourselves into a cleaner, greener and more resilient future. And that, I think, is largely where, as a physical scientist, my role stops, and as an engineer's, your role takes over. But I think it is clear from all the analysis that I've done and that I've seen that if we are really going to respond to this challenge, there's not going to be one single solution. There's going to need to be action on a whole suite of different areas. And so if I've got one summary of where I see the challenge, it's this. This is a photo of my kitchen sink, and it seems to me that it's kitchen sink time. We need every different technology to be tried and developed because the challenge is huge and the time available is really, really short. Thank you.